Okay, welcome back everyone. So today I'm going to do a video about Lagrange multipliers, and I'm going to begin the video with kind of a more rigorous reasoning for why Lagrange multipliers work, which I'll kind of remind you of in a second. And then I'm going to go on to a nice example, which involves some geometry of a Lagrange multiplier problem, which I want to share with you. So first, let's start off again with the more rigorous reasoning for Lagrange multipliers. It's more rigorous than what I described in the previous video on Lagrange multipliers. So why don't we begin? So first, I'm going to kind of describe constraint, or I'm going to remind you what Lagrange multipliers state, which is that given some, and we're going to work in 3 dimensions here, given some multivariable function f of x, y, we want to maximize this function given the constraint g of x, y equals c. So this is some level set, right? G of x, y equals c. Okay, and the Lagrange multiplier states that the maximum value xm, ym, the ordered pair xm, ym, occurs at the following. It occurs when the gradient of f of xm, ym equals some is basically it's parallel to the gradient of g at xm, ym. So we want to prove that the gradient of f at this maximum point, constrained maximum, is going to be proportional or parallel to the gradient. Parallel would be a better word, to the gradient of g at xm, ym. So this is what we wish to prove. Okay, well, how do we do that? Okay, well, let's look at what the properties of the, or what a property of the constrained max is. And let's also look at this visually. So if we look at the constrained max, here, well, again, I'm going to draw a little graph, which will hopefully illustrate it. Okay, that's not the best graph, so I'm going to erase it. I don't have many high hopes for drawing a nice graph, though. Okay, that's good enough. So this is our multivariable function f of x, y. And then let's draw our level. So let's say our level is something like this. So that is our g equals c. Okay? Now, let's see what we can do here. So at our constrained max, let's say our constrained max is here. So this is our magical point xm, ym. So this is at xm, ym. And then obviously f of xm, ym, but it's not very necessary right now. Okay. Well, notice that if we move along this level, that's projected onto our multivariable function, it's only going to decrease from here, right? Because this is our constrained max. So it's kind of a local max here of the function, given this constraint. Well, it is the absolute max of the function given this constraint. So if we move in any direction here, and these directions are going to be tangent to our level, so we're going to call those directions u hat, and you'll see why in a second, then it's always decreasing. But at the xm, ym, we have that the function is actually it's not increasing nor decreasing. It's staying the same. Therefore, the rate of change of the function at xm, ym is actually 0, but only in the allowed directions, which are the directions that are tangent to our level projected onto here, right? So this tells us that df ds in the direction of u hat which which are the directions that are tangent to our level, has to be 0. Okay, at x and y, I should say. Okay, well, by our formula that we derived in one of the previous videos, this is going to be equal to the gradient of f at x and y dotted with u hat. But that tells us that these are perpendicular, and u hat is tangent to our level set here. And that tells us that the gradient of f is perpendicular. That tells us that the gradient of f is perpendicular to our level g equals c. So gradient of f, just think that it's at x and y. Just think that in your head. It's perpendicular to the level g equals c. Okay, at x and y. Okay. Well, what else is perpendicular to the level g equals c? Well, by a fact that we proved in a previous video, the gradient of a level, well, let's take this example. So the gradient of g is going to be perpendicular to its level, to any level of g. So that tells us that the gradient of g is also perpendicular to g equals c. Okay. Well, that tells us that since both of these are perpendicular, then they're parallel. Therefore, the gradient of f is parallel to the gradient of g, which is what we wanted to prove. So this is exactly what we wanted to prove from what Lagrange multipliers state, and that's going to finish this proof. So I'll just clear the board and write down the problem that we want to work out next, and I'll see you then. Okay, so we're back, and here's the problem. So our goal here is to minimize the surface area of a triangular base pyramid with a given base and a given volume. So first, I kind of, prior to recording this, I drew a bit of a coordinate system and what we're working with here. So I labeled this vertex here, P1, marker's not working. Then this vertex here, P2, this vertex here, P3, and this vertex here, P. Okay, and I'll just note the coordinates of P to be x, y, and then some height h. Now, I'm going to note that this height h has to be constant, and let me explain that quickly. So the reason it's constant is because of the fact that we have a given volume and a given base. So note that the volume, and the reason being is that note that the volume of this pyramid is going to be equal to 1/3 times the area of the base times the height, right? But we're given that this is constant, so this is given, and also this base is given. Therefore, since we can solve for h, then our height is also constant, or given, technically. It's not directly given, but it's indirectly given. Okay, so further note that, well, maybe at first glance, you might think of calculating the areas of these triangles by using cross product, namely the fact that the areas are equal to, so we can say AIs, so the AI of each triangle on the side is equal to 1/2 times the magnitude of, let's just say, PI, let's just say PI and then the vector from PI to PI plus 1. This isn't that rigorous, but it'll get the job done. Cross with, well, the vector from PI to P. So that might be what you would think of at first glance, but minimizing this is a real pain. So, and in fact, it won't work. So that's not going to be the method we're using. Okay? Now, the method we're going to use will involve a different perspective. So first, what we want to think of is projecting this point P onto the xy plane, and we'll call this point Q. Okay? And note that it will have coordinates x, y, but zero. Okay? So now I'm going to take a closer look at this triangle on the xy plane that we've produced. So we have P1, P2, P3. And then we have our Q, which is not necessarily in the middle. Okay? Now I want you to consider how else, and what other way we could calculate the areas of these triangles. And you'll note that let's try to involve height here. So we need to get the heights. In a nice way, we need to get the heights of each of these triangles to minimize the variables that we produce. So to do so, well, let's think of Pythagorean theorem. So if we think of the height here, let's think of how we would get that. Well, we can get that by finding this length here that is drawn. So for example, for this height from the triangle P1, P2, P, to get that height, we already have this side of the right triangle. We just need to find the length from Q to this P1, P2 line and make it perpendicular to form a right triangle. So what we have here is that, well, I'm gonna write this length as A1, and then I'm gonna write this length as A3, then this length as A2. Okay, and now let's compute the corresponding heights of each triangle. So that's pretty simple, right? So our heights are, so for the first one, it's going to be the square root of, well, we have A1 squared plus H squared. And it's important to note that, well, later on we'll use this. It's important to note that H, again, is a constant, but A1 is a variable because we need to figure out what A1, A2, and A3 to choose such that we minimize our surface area or side surface area of a triangle, since the base is on the xy plane, which we can think of as the ground. So we don't have to worry about that. And in fact, that's going to be the base. The area of the base will come in helpful as a parameter to use Lagrange multipliers. And the other heights are analogous. I'm not going to write them out. They're just going to be A2 squared plus the square root of A2 squared plus H squared and the square root of A3 squared plus H squared. Okay, well, now how would we calculate the areas of each of them? Well, we still need the base, right? But note that we can just assign variables to the base easily because the bases are constants. Reason being, again, is that the triangular base is given, so the bases are fixed. So we can write this as base 1, base 2, base 3, and transfer to here. Base 1, base 2, base 3, B1, B2, B3. So our areas, I'll write it as the sum of each of these sides, each of the areas. So, and we'll call that function, and again, it's in terms of A1, A2, a function of A1, A2, and A3. Call it f of A1, A2, A3, as 1/2 times the first base, B1, times the first height, square root of A1 squared plus H squared, plus 1/2 B2, square root of A2 squared plus H squared, plus 1/2 B3, square root of A3 squared plus H squared. Okay. Well, again, this is not enough to use our Lagrange multipliers. We still need our constraint, which can be some g of A1, A2, A3 equal to some constant. Well, again, the base is constant. It's given. So how do we calculate the area of the base? That will be our constraint that I mentioned earlier. Well, what I'm going to do is I'm going to take a look at the base again. I'll use the same triangle. Might be a little less clear, though. And I'm going to split up into these parts. So I'm going to draw a line from Q to each of the vertices, P1, P2, P3. Now we can find the area of each of these three triangles that are formed when we do this. Right here, I'll give a clearer image of what we're doing here. So this is our point Q, and we're splitting up into these three triangles, right? But the nice thing is that we already know the heights of these. We already assigned those variables to A1, A2, and A3. We also know the bases, B1, B2, and B3. In other words, our function g of a sub 1, a sub 2, a sub 3, which is constant, so it's some constant c, and it's going to be equal to a1, sorry, I should give it's the area, so it's going to be 1/2 a1 b1 plus 1/2 a2 b2 plus 1/2 a3 b3. Maybe I should have used summation notation to be a bit more concise, but we're only drawing out 3 terms, so it's kind of not very fruitful. Okay, so now we're ready to use Lagrange multipliers. So the nice thing is that it might look complicated, but the Lagrange multipliers are going to be very symmetric here, because if you look at these terms, they're all very symmetric. The only thing that we're replacing here is a1, a2, and a3, and the rest are just constants. So if we look at the first one, let's calculate the partial derivative of f with respect. I'm not going to calculate the full gradients of each. I'll let you do that as an exercise, but it really is symmetric. So once we calculate the partial derivatives of each one with respect to the first variable, namely a1, the rest will follow from that. We'll just replace the a1 with ai. Okay, so partial derivative of f with respect to a1 is going to be equal to, well, we just focus on this because the rest are constants and they go to 0. So 1/2 b1 is a constant, we bring that out, and when we take the derivative of this, we use chain rule. We have 1/2 times the root of this, so the root of a1 squared plus h squared, but all multiplied by the derivative of the inside, which is 2a1, which is just 2a1. So note that we're just going to have 1/2 b1 times 2a1 over the square root of, over 2 times the square root of a1 squared plus h squared. Okay, the 2's cancel. So we're just going to be left with this 1/2. So we're going to be left with this a1 b1 over 2 root a1 squared plus h squared. Okay? Okay, so now, again, the rest follow from that for f, and we have that the partial derivative of g with respect to a1 is equal to, well, that's much easier. It's just 1/2 b1. So now let's set these equal to and involve the Lagrange multiplier. So we're just going to set a1 b1 over 2 root a1 squared plus h squared equal to the Lagrange multiplier, so lambda times 1/2 b1. But since b1 and all bi are non-zero, we can cancel the b1 and cancel the 1/2. So we get that lambda is just equal to a1 over the square root of a1 squared plus h squared. And actually, you'll see that we can solve for lambda for each of these since it's symmetric. So this is going to be equal to lambda, which is also equal to a2 over square root of a2 squared plus h squared, which is also equal to a3 over the square root of a3 squared plus h squared. Now, it's pretty intuitive to see that this implies that a1, a2, and a3 are all equal to one another, but I'll quickly give an idea for why that's the case. So to understand, well, I'm going to integrate this entire equivalence, okay? And I'm kind of running out of space, so I'm going to have to get rid of some things. So I'll just get rid of this. So this is what we have. This is really the only important thing right now. Okay, we'll start from the top. So we're going to consider the first two equations. So let's actually solve for a1. So in doing so, we're going to cross multiply, and that will simply give us a1 times the square root of a2 squared plus h squared equals a2 times the square root of a1 squared plus h squared. And squaring both sides gives us, and then also multiplying this term out, well, this becomes a1 squared, and the square root goes away. So we're going to have a1 squared times a2 squared plus a1 squared times h squared equals a2 squared times a1 squared plus a2 squared times h squared. And notice that these two terms are the same by the commutativity of multiplication, so we can cancel those out. And solving for a1, we actually get that a1 squared equals a2 squared. And when we take the square root, we get that this implies that a1 is equal to a2. We're not going to consider the negative case since lengths are non-negative. That's why, because we can't have negative length in geometry. Okay, well, the same thing can be applied to show that with these two equations, or these two equations, and show that a3 is equal to this. I'll leave that as an exercise to you, a very trivial exercise, doesn't even involve calculus. So, in fact, that finishes our problem, and this is the solution. So, in other words, the point Q is going to lie in the incenter of our triangular base, and thus the point P will lie above it. Okay, well, that finishes the problem and also the video. So, have a nice day and goodbye.